So today's lecture considers to the aldehydes and ketones. So this group of compounds is very large, and here are many compounds that have pleasant odor that are responsible for the fragrant odor of many fruits and perfumes. For example, it can be cinnamon, aldehyde, civetone, formaldehyde, and so on. And many biological active compounds the same have aldehydic or keto group. For example, ketones such as testosterone and estrone are known as sex hormones in animal bodies and the same in human body. Here at this slide, you can see some examples of compounds with carbonylic group. For example, this one compound, civetone, is responsible for the musky odor of this animal, is this civet. Cinnamaldehyde is responsible for the odor of cinnamon. And the same here, we have example of sex hormone. It is man hormone testosterone. And here you can see picture of a man with optimal testosterone level and person with low testosterone level. How we can classify these compounds? First of all, we can divide them at aliphatic, alicyclic, and aromatic. The same, we can divide aliphatic at saturated and unsaturated. And depending on the group, we can have aldehydes and ketones. We can see it at the next slides. Isomerism can be connected with a group. For example, here we have ketone, here we have isomeric aldehyde. So we have different functional groups. Here we have structure isomerism, and here is another position of carbonylic group. So this is positional isomerism. On the next slide, we can see the isomerism connected with different structure of hydrocarbon chain. So it is skeletal, or here we have straight hydrocarbon chain, and here we have branched hydrocarbon chain. The same at this example. This part is straight, and this part is branched. How are formed names? If we have aldehyde, we drop final E from the name of appropriate alkane. For example, methane, we change this E and add al, methanol, ethanol, propanol, butanol. These are names according to UPA. But many aldehydes have trivial or usual names depending on the names of appropriate acids or depending on the source. For example, formaldehyde is named because there is formic acid. Acetaldehyde derived from acetic acid, and so on. Similarly, with more difficult compound, here you can see the priority of aldehyde group. So, aldehyde group has higher priority than alkyl substituent. We start numbering from this side, and it will be 3-methylbutanol. Higher priority than double bond. We start from this side, and higher priority for from hydroxy group. Here are examples of compounds with cycles in the molecule. Here is saturated site cycle, so it is alicyclic compound. And if we have such a molecule, aldehyde group is named in the suffix as carbaldehyde. Carbaldehyde. If we have aromatic ring, benzene ring with attached aromatic group, it has specific name, benzaldehyde, and this name is used in UPAC. This salicylaldehyde, it is trivial name, and normally it can be used, it can be named as 2-hydroxybenzene carbaldehyde. And for benzaldehyde, the same. UPAC has, according to rules, special name, benzene carbaldehyde, but still in use is benzaldehyde, and it can be used in UPAC system. For ketones, we have ending on, suffix on. Propanone, butanone, pentanone, and we mark the position of this carbonylic group. Here is example with cyclohexanone. Here, carbonylic group has priority to the methyl group, to the alkyl substituent, to the double bond. And if we have such a molecule, we can name it as derivative of propan. So it will be phenyl propanone 2. Or another variant how we can give the name, we divide this molecule at two parts. It's one part, another part, and it will be methyl group, this is phenyl group, and we add the word ketone, methyl phenyl ketone, or acetophenone, it is trivial name. Benzophenone is trivial name. Some aldehydes and ketones that are very important and are used very widely. The first member in the aldehydes triad is formaldehyde. It's synthesized from methanol in industry by oxidation in high temperature. It is gaseous compound by around at room temperature with boiling point minus 21 degree. But it can be dissolved in water. The highest concentration is near to 40%. Sometimes you can meet the number 40% aqueous solution. And this solution has specific name, formalin. It's used as disinfectant, preservative, and the same. This compound can be used for manufacture of plastics, building insulation, particle board, and plywood. Acetaldehyde. This aldehyde that is obtained by oxidation of ethylene, but the same can be obtained by reduction of acetic acid or oxidation of ethanol. It's liquid at room temperature, and the same it's used for acetic acid preparation. Acetone, the most important ketone, is used as solvent because it's a good solvent and can be mixed with water in all concentration. Industrially, it can be synthesized from isopropyl benzene by oxidation, and next by acidification. And this process gives advantage because are synthesized two very important compounds. One is phenol and another acetone. One more important compound, it is bisphenol. Bisphenol can be used from acetone, synthesized from acetone, and it's a very important inorganic synthesis compound. So how can we synthesize aldehydes and ketones? Some methods are familiar for you. For example, oxidation of alcohols. Depending on the position of hydroxy group, it can be obtained or aldehydes if it is primary alcohol, or ketones if it is secondary alcohol. And as oxidator can be used for many oxidators, but one of them that is important, it is pyridinium chloroformate. It is complex compound from pyridine, chlorides, and chromium 6 oxide. Next method, the same is familiar for you. It is Friedel-Crafts acylation. The catalyst in this reaction is Lewis acid, and the type of reaction is substitution electrophilic. Kucherov's reaction, it is hydration of alkenes. If we have acetylene, by hydration we obtain acetaldehyde. In case of another alkenes, we obtain ketones. And the catalyst in this reaction is lead cation, mercury cations. Hydroformylation, it is industrial process. Here as reagent is used the mixture of CO, gaseous, and hydrogen. And as a result, in molecule appears aldehyde group. And the same, this group can have name formic group, formyl group. So it's the reason why reaction has name hydroformylation. The same, this method is familiar for you. Here are hydrolyzed dihalogen derivatives. Depending on the position of these two halogens, we obtain or aldehyde or ketone. Such type of dihalogen derivatives are called gem halogen derivatives. And one more method, that is pyrolysis of carboxylic acid salts. The same, depending on the starting compound, we can obtain aldehyde. If it is mixed salt of some carboxylic acid and formic acid, then is formed aldehyde. Here is evolved calcium carbonate. And if we have another carboxylic acid salts, then a formic, then it's formed ketone, and the same is evolved calcium carbonate. Physical properties of ketones. We can say that they have medium position. You can see here at this picture. Here is alkane ether, here is aldehyde and ketone, and here is alcohol. If we compare the boiling point, here we can see increasing of boiling point. So the medium position of boiling point, it is because they have high polarized group, such as carbonyl group, But aldehydes and ketones are not able to form hydrogen bonds between their molecules, such as way as can form alcohols. But they can form hydrogen bonds with another molecules that have NH or OH bonds, such as water or amines. So the reason this medium position is that they are more polarized, and between molecules are dipole interaction, but there are no hydrogen bonds, and they don't interact in such strong way as alcohols, for example. Here you can see example how interact ketone or aldehyde with water molecules. So here we have polarized bond, partial positive charge at carbon and negative charge, partial negative charge at oxygen. And the same here in this molecule, OH bond is polarized and partial positive charge is at hydrogen. And here is possibility for the formation of hydrogen bond between the molecule of aldehyde of ketone and water molecule. It's the reason why lower aldehydes and ketones are miscible with water, are water soluble, but if we have this R longer, then they are not miscible with water, not water soluble. But the reason is in this hydrocarbon chain. Infrared spectra of aldehydes and ketones give a strong vibration in this area 1710 some reverse centimeters, and in aldehydes we have this shift, specific shift for CH bond near this number of reversible centimeters. The same if we have conjugation of carbonylic group with double bond, this stretching, this signal is shifted to lower numbers. If we have conjugation with aromatic ring, the same, we have shifting to the lower numbers. In NMR spectra, we can expect to find the signal of aldehydes group protons near 9 to 10 particle per million, and alpha carbons can be at 2.4, for example. Here is example of an NMR spectra of butanol. This signal is for aldehydic group proton, for this proton. Here is formed difficult spectra, yes, with many signals from this alkyl substituent. Here, these two protons give triplet, 3 signals, and here must be a single doublet, 2 signals, and the more signals must be here. That's maybe this one. Here is the table with physical properties of aldehydes and ketones. First of all, we have aldehydes, the first member. You can see that boiling point is 56 degree. And what compound are liquid? We can see here, whereas melting point higher than room temperature. It is acetophenone. Then this one, propionophenone, benzophenone. So this compound will be solid at room temperature. And all these compounds will be liquid at room temperature. Similarly, aldehydes, almost all will be liquids at room temperature. Only formaldehyde or methanol is gaseous. Carbonyl group. It's important to understand the structure of carbonyl group. So the distance in CO bond is 1.24 angstroms. You can see that this distance is lower than in alcohols and ethers. The reason is that this bond is double. And the reason is that oxygen is strong electronegative atom. And this electron pair is shifted to oxygen. Here is formed partial negative charge. At carbon is formed partial positive charge. And here this arrow shows the polarization of the carbonyl group. And here we have the resonance structure between this form where we have double bond and this form where we have positive charge at oxygen and negative charge at carbon. And in real condition, we have something in between. This picture shows the electrostatic map of aldehyde molecule. Here is oxygen atom. Here we have higher electron density, and here we have lower electron density. The same here is shown how are situated sigma bonds around this carbon in carbonyl group. You can see the degree, the valence angle is 120 degrees, and the hybridization state of carbon is sp2. And non-hybridizated orbital is in a perpendicular plane and forms a pi bond with oxygen. So what type of reaction are possible for carbonylic compounds? The first type is nucleophilic addition to carbonyl group. Then there are reaction of addition, electrophilic addition, elimination with immunocompounds or nitrogen-containing compounds. Next group are a substitution in alpha position to carbonyl group, and oxidation and reduction. So let us discuss all these types of reaction. First of all, nucleophilic addition is very important group of reaction. Nucleophiles are particles that have negative charge or partial negative charge or high electron density in some places of molecule or unpaired electron pair. And the place where this nucleophile can attack carbonyl group is that place where we have partial positive charge. So as a result of this addition and this attack, we have nucleophile added to carbon. Then hybridizated state of carbon is changed. Here carbon is sp2 hybridizated, In this particle, carbon has sp3 hybridization state and negative charge at oxygen. And then hydrogen, proton from water is added to this negatively charged oxygen. If we have a weak nucleophile, we need to increase the strength of this reagent. Then reaction with some nucleophiles will be better in the presence of proton. The reason is that proton is attached to carbonylic group oxygen, and here is formed fully positive charge at carbon, not partial positive charge, but fully positive charge. And then the attack of nucleophile is more efficient. So some nucleophiles we can classify as those that add reversibly to the carbonyl group and those that add irreversible. And here you have a list of some examples. Irreversible carbonylic compounds react with Grignard reagent and acetylides. And reversibly, they react with water, alcohols, and HCN. This means that this compound form weak nucleophiles, and we need to increase the strength of carbonylic compounds in this reaction by addition of hydrogen. In case of water and alcohols, we can add proton. In case of HCN, we will use alkali medium to increase the strength of nucleophile. And here I added links for Wikipedia about leaving group and conjugated acids that helps you to understand better this paragraph. If we talk about reactivity of ketones, we can say that they are less reactive. And there are two reasons. The first reason is steric. It means that we have more groups around carbon atom, that is the goal for nucleophile attack. And another reason, electronic, means that any alkyl group that has positive inductive effect will decrease this partial positive charge that we have at carbon atom of carbonylic group. And this reason decrease the reactivity of carbonylic compounds. And here I have short clip about attack of nucleophile. Here we have formaldehyde. This is hydrogen, this is carbon atom, this is oxygen atom, and this is pi bond. Here are shown unhybridizated orbitals only. So you can see that nucleophile, sorry, back. Yes. How nucleophile attack this carbon atom. At next slide, we can see aldehyde. So this is alkyl group, and the attack with nucleophile. You can see that this group disturbed. And so from this side is difficult, from this side is better to attack. And if we have ketone, from both sides, from carbonylic group, is difficult. Only here in the middle, the attack will be effective. It's the reason why ketones are less reactive than aldehydes and formaldehyde. And here we have examples of addition to carbonylic group. Here, first example, it is formation of hemiacetals and acetals. These are product of reaction between aldehydes or ketones with alcohols. As I said at the previous slides, this reaction is reversible, and catalyst here is protons that increase the reactivity of aldehyde or ketone. So this red part is added to oxygen, and hydrogen is added to, this red part is added to carbon here, and this hydrogen is added to OH group, such a way. And this is added to carbon. And then next step, if we have exceed of alcohol, then the next molecule react with OH group here in hemiacetal and is formed acetal. This second reaction is similar to substitution nucleophilic, similarly as are formed ethers. The same, they are formed in acidic medium. Addition of water as result of water addition are formed hydrates. And these compounds are not stable. We can isolate this compounds from the solution. There are some exceptions when we have strong electron void driving group in hydrocarbon chain. For example, if here in 3-chloroacetaldehyde we have 3 halogen atoms. I'll write the structure of this compound. It was used as sedative and hypnotic agent. Nowadays, it's not used as medicine, but still is used in veterinary. This reaction is familiar for you. It is reaction with Grignard reagents. But I propose to make a break and then we continue with next part.